Our goal in this series of lesson videos will be to complete our characterization of the probability calculus. And we'll start with the notion of conditional probability. So in this lesson, our hope is to develop a basic understanding of conditional probability and then define conditional probability with a formal rule and figure out how to use that. The idea behind conditional probability is that the probability of a statement being true can vary depending on certain conditions, certain other statements being true or not. Sometimes we want to know more than just the probability that some statement P is true. We want to know the probability that P is true given that some additional statement Q is true. Or to put it another way, we want to know the probability that P is true on the condition that Q is true. For example, an engineer might want to know the probability that the part on a machine will fail given that it has a defect. This is a conditional probability. Let's look at an example to give you a bit of an intuitive feel for how conditional probabilities are determined. Suppose there are 200 men, of which 100 are smokers, and 100 women, of which 20 are smokers. What's the probability that a person chosen at random is a smoker, given that the person is a woman? What we want to know is what proportion of the women are smokers. Well, we know that there are 100 women in the group of 300 people, and 20 of them are smokers. That should lead us to expect that the answer is going to be 0.2. And that's right. But what does that answer mean? How are we getting to that? Let's write out this reasoning. We wanted to know the probability that a person is a smoker given that they are a woman. It's going to be some fraction of the women. So we'll divide by the proportion of the group that are women. Divide what? Well, we wanted to focus on the people who are women and smokers, which was only 20 of the 300 people. So running the math, we get the chance that someone who is a woman is a smoker to be 0.2. That example should start to give you a feel for the rule that governs conditional probability, but we want to state it formally. First, we need to introduce some new notation. So in the context of probability, a vertical bar means given or given that. So PR of P bar Q is how we write the probability of P given Q. We can now give our rule for the probability of P given Q. And note that it's going to come in two parts. The first part tells us the formula we will use to determine conditional probabilities. And we can use it whenever the probability of Q is greater than 0. So the probability of P given Q is determined by the probability of the conjunction of P and Q divided by the probability of just Q. So think back to our previous example. We had the probability that a person in the group was a woman and a smoker on top. That was the probability of a conjunction. And the probability that the person was a woman on the bottom. And that was our condition. That gave us our 0.2 number. So even going intuitively, we were starting to follow this formula. The second part of our rule tells us that conditional probability isn't always defined, however. If there's no chance that the condition sentence is true, so its probability is 0, it doesn't really make sense to define the probability of P given a sentence that's impossible to be true. Besides, we can't really divide by 0. So the probability of P given Q is undefined if the probability of Q is 0. How can we make further sense of this rule? First, we have to start with our condition sentence Q having a non-zero probability, so that's the only time we can apply this formula. So there have to be some circumstances that make Q true, and that's given by this green shaded circle. Well, some of the circumstances that make Q true are also going to be ones that make P true, at least most of the time. So that's where the conjunction of P and Q is true. And remember from when we looked at these Euler diagrams before, the conjunction is given by the overlap of the circles. What we're interested in, though, with conditional probability is the chance that P is true given that Q is true. So we start by restricting ourselves to the conditions where Q is true in the green circle. Then we ask, what proportion of those are also conditions where P is true? So in terms of this diagram, the conditional probability of P given Q asks us to determine what proportion of the Q region is also a P region. So what's the ratio of the overlap to the total Q region? Now let's work on using this formula in an example. We're going to go back to our case with 300 people, 100 women, 20 smokers among the women. But we're going to ask about a different conditional probability this time. Now we want to know, what's the chance that a person is a woman given they're a smoker? First, it's always useful when determining probabilities to establish the component statements we need. So here we want to ask about the probabilities around W and S, where W is the person is a woman and S is the person is a smoker. So we want to know the probability of W given S, the probability that someone is a woman given that they're a smoker. Substituting into our formula, we get the probability of the conjunction, someone's a woman and a smoker, over the probability that they're a smoker. The probability of W and S being true is 20 out of 300. 20 of the total 300 people are both women and smokers. The probability of S is 120 out of 300 because there are 120 total smokers, 100 men, 20 women. Simplifying the fractions for the probability of S and the probability of W and S, plugging them into our formula, we have 2 out of 30 on the top, 2 out of 5 on the bottom, and that gives us that someone has a 1 in 6 chance of being a woman if they're a smoker. Now, part of why I used this example again, but asking a slightly different question, is that contrasting these two questions reveals something important about conditional probability. The order of what sentence is true given which other sentence is important. It matters the order. So usually the probability of P given Q is going to be different from the probability of Q given P. So the probability of P given Q tells us assume Q is true. Then it asks you the probability that P is true given that assumption. The probability of Q given P tells you assume P is true. And then what proportion of the time is Q true when P is true? So in the example of our population with some smokers in it, the probability of being a smoker, given that one is a woman, that was our first example, we had the probability of S given W. That was 0.2. Contrast that with the probability of being a woman given that one is a smoker. That's lower, actually. So the probability of W given S was 1/6. Paying attention to the order when you use the formula will make sure that you get the right answer. So now we have a definition of conditional probability. Note that it depends in part on the probability of a conjunction. But what we still don't have is a general rule for determining the probability of a conjunction. In these examples, we just brute forced it by counting the number of people that had both of two properties. But in the next video, we'll look at a general rule for conjunction.